and welcome to the video on extreme values. So I'll start off with a couple of definitions. So what are extreme values? What does that mean? So extreme values are basically minimums or maximums, So minimums or maximums, maximum values that is, on a graph or function. On a graph or function. Okay, and optimization, this is a kind of new word, optimization. Okay, this isn't just thinking hopefully or positively, but it is the process of finding these extrema. Okay, so process of finding these extrema. Alright, so those are the two definitions, and that's basically the overarching concept of this video. So let's say we have a function. Okay, so if f of x is some function, okay, is a function in some interval, we're just going to call it I, and then at a, and there we go, and at a is in I. Okay, so this point A, sorry, I got all these variables going, but A, this is an x value in the interval, which is given by like a range of x values. Then we have an absolute minimum. So here's where we're gonna get into the what are extrema, right? So if f of x is a function in the interval I, and A, I'm just gonna get rid of that at, and A is in I. So first of all, let's draw what we're explaining here. So here's our x and y graph. Here's our, let's say this is the interval I, okay, on the x graph. So this is I in here, and A is somewhere in there. All right, so let's say A is here. Okay, so that's what I've explained so far. And then we're going to say, and A is in I, then we have an absolute minimum. We're going to go over first. Absolute minimum f of A of the function f of x on I if, this is a big if, okay, so this is the important part, f of A is less than or equal to all other f of x for all x in that x interval called I. Okay, so what this means is that at A there's an absolute minimum. So let's say f of A is here. Okay, so that's the height f of A. Okay, and then everywhere else on this interval is higher or is above that point. Okay, so on that interval, we can draw it here. So here's the interval. A is the lowest point because all of the other f values go up and above, right? So something like that. So this defines our absolute minimum. Okay, and conversely, let's say we have an absolute maximum. And again, the beginning is the same. So if f of x is a function on the interval I, and A is within I somewhere, so then we have an absolute maximum f of A of f of x on the interval I if we have that f of A is now greater than or equal to f of x for all of the x in the x interval called I. Okay, so this is basically telling us the opposite, right? So here's our graph again, and now we have the interval I, same thing, so interval I, okay, and A is somewhere in there, okay, and let's say this is the point f of A, all right, so this is height f of A, that's the value of our function, and for the rest of the x values on this interval, for the rest of those, the function values have to be equal to or less than that maximum. So here it's going to be less than. And then here I'll even draw one like kind of equal to, right? So on this interval though, we don't see anything that goes above this level here, right? So that must be our maximum. That's the highest point. It is notable to recognize that functions may not have maximums or minimums. So I'll write that down. So functions may not have, and I'll abbreviate minimums or maximums if if, I'll just squeeze in the if there, and if we have two cases. So one is that if f of x has a discontinuity, so if it's discontinuous at some point, so that would look like if we were to have something like x and y, and then we had a graph going along, and this was a and this is b. This defines our interval I, okay? And then for some point, so we're going along, and then this looks like it could be the maximum, but it has that discontinuity there, and it jumps down here. So here we can't really, like, it's kind of confusing, and it's discontinuous, so we can't really do anything with that. We can't declare this the minimum, that the maximum, or this the minimum either. Okay? So if f of x has discontinuity, we may not have a minimum or maximum. Or if number 2, if our interval I, okay, is open. So what does that one mean? That means that let's say we have a graph such as the following. So we have something like that, and A and B are here. So those are the endpoints to our interval, right? And I'm just drawing the interval lines. Okay, so let's say we have an open dot there, and then it continues on downward, and it goes down, down, down to infinity. There's an asymptote, a vertical asymptote at B. So here we can't declare that there's a maximum here or minimum down there somewhere, because we don't even know if it ends, right? So there is no minimum or maximum at the endpoints on A, B at all. Okay? All right, so that's where functions may not have those extrema at all. So this leads us to the extreme value theorem. Extreme value theorem, which is basically a theorem that says if we do have a function, so if f of x is continuous, I'll abbreviate, on a closed interval, so that eliminates the possibility of having open intervals, right? On a closed interval, and we'll just call it a to b, I is equal to a to b, all right? And that's a closed interval, so that means including endpoints. So this is, we're going to say the theorem says it takes on both a minimum and maximum value on the interval I. So on I. Okay? So that's a very important theorem actually. So we're saying if f is continuous, so that eliminates the whole possibility of having a discontinuity, and we're saying on a closed interval, so that eliminates the whole open interval thing, which could lead to no extrema at all. So if both of those conditions are fulfilled, then this function takes on both a minimum and maximum value on the interval we're looking at. Okay? Alright, so now let's go into something called local extrema. Okay, so again, extrema just means minimum or maximum. So, and the important term here, the new one we're going to learn, is local. So what does local mean? Local, when you talk about local in everyday life, you're talking about oh, do you live locally? So it means around the area, right? So in the surrounding area. So what we're going to have is, let's say we have a graph that looks like this. So we're going to have something like that, and it goes down a little bit and comes up and keeps going on. So what is a local minimum? So local minimum, so there's a local minimum, I'll abbreviate, at some x equals, let's say a, if f of a, if the value of that function at that point is a minimum, is already a minimum of f on some open, this is important, some open interval, not a closed interval, but an open one, containing a. Okay, so what does that mean? So local minimum, so let's look at this point here. Okay, it looks like a low point, right? So let's say this is point A, all right, on our x and y, on the x. And what that means is that if we have some open interval around it, so that would be denoted by rounded brackets, right? So on this interval here, it is the lowest point, right? So that means right in the vicinity Like what I like to do for local things is draw like a little rectangular box around it, right? And inside that box, it is the minimum, right? It is the minimum value of that function. So this one is a local minimum here. Okay, so conversely, let's say we have a local maximum. So what does that mean? So I'll box this one. So that's a local minimum. And now what is the local maximum? So that is local max at, we're going to say x equals c, if f of c is, it's going to be the same thing, is a maximum of f. We're just going to replace minimum with maximum of f on some open interval, and this time containing c. Containing, and then c. Okay, so pictorially, on our graph here, let's look at this one. This one looks like a maximum, right? Just right around it. So let's say this is point C, all right? And then we draw our little like open interval. So right around it, so we're going to draw that, sketch the little like rectangular box, right? So something like that. And we see here that inside the box, yes, this is a maximum. So this is a local maximum. So I'll just label it local max. And the one that we did before was a local min, right? And now you might be thinking, well, that is the highest and lowest points, but we also see something here, right? This looks kind of like a little hill, right? Even though it's not higher than this one, it could still be a local maximum, because if we pick this point, let's say it's, I'm going to label it B, okay? So we're going to kind of create an open interval here. So we're going to form that little rectangular box around the point, around the graph there at that point. And yes, in this box, it does look like a maximum, right? So this is also a local maximum, even though it might be overshadowed by this guy over here because it's higher, but we're not in that area. I didn't extend the interval that far left. So in this little interval right around the area, right locally, right? So locally around B, this is a maximum. So therefore, it is a local maximum.